Hello, everybody. Hello, everybody. I am John Turner. It's nice to be here today. My talk is on optimization concepts for data scientists. I hope you enjoy it. But before that, I just want to say a few words about the Merage School and the Master of Science in Business Analytics. I do teach in this program. I teach the core management science class, which deals with optimization and simulation. I think it's a really nice program. It's been around for a number of years now. It's a full-time one-year program. It is STEM designated, which means that if you're an international student, you can work in the United States on an OPT visa for 3 years after graduating. The program begins every summer. It goes for 5 months. You have the option to, let's say 5 months, sorry, 5 quarters. You have the option to, start in the summer and then end at the end of the following summer, or end in the spring if you wish to graduate, at the end of spring. So there's opportunities to work with industry partners. I also supervise students as part of a capstone project that spans 8 months. I've worked on a number of these over the years. And there's a number of classes within the program that you will find interesting. They span the gamut from data analytics, marketing analytics, and operations analytics. And in fact, these are 3 separate tracks within the program. So if you're interested in, say, focusing on operations, which is my specialty, you can certainly do that. But if you're more inclined to focus on big data and natural language processing and things like that, you can do the data analytics track. And we also have some really great marketing professors that teach classes in the marketing analytics track. So it's worth pointing out that we have a number of companies that work with us on projects. These are world-class companies like Ingram Micro that are local to the area. Experian is also their U.S. headquarters is based locally, and a number of other companies in the sort of metro LA area as well, because we're here in Irvine. We're basically driving distance from Los Angeles. All right, so what else? This next slide just shows you a number of companies that our alums currently work for. So there's good networking opportunities if you do decide to take a program such as our Masters of Science in Business Analytics. And if you're interested to know more, you can get in touch with us in any of these 3 different ways. I am told that there is a Merage booth here at the DSGO conference today. All right, so that's my little promo. Let me jump right into the actual talk. So the talk today is on optimization, and so optimization is a type of prescriptive analytics. It's probably the most common methodology used for solving prescriptive analytics kinds of problems. But I'm going to do just a quick review just so that everybody's on the same wavelengths today about what is optimization. And then I want to share with you why I believe it's important to data scientists. And there's a few reasons, but one in particular today. And then I'm going to take you through 2 different concepts. These are things that I learned through various industry projects over the years to look out for. And so we can talk a little bit about that afterwards too. Okay. So what is optimization? Well, optimization is really a way to formulate it's essentially a problem that the computer is going to solve. You have an objective function that's here denoted by f of x. And so the computer is going to pick values of x and try and minimize or maximize that function f of x. And if it was only an unconstrained function, then this problem would be somewhat easier. However, in practice, we often have resource constraints of different kinds. You could have inequality constraints or equality constraints, and you may also have other types of constraints, such as the variables must be integer. Maybe they need to be binary to denote decisions like, yes, open a factory over here, or no, do not open a factory over there. And so there are a lot of different uses for optimization. Simply put, if you're a business and you want to try and maximize profit, maximize revenue, minimize costs, you will be interested in solving an optimization problem. And I have here on the screen just a few examples from my own experience. I did some work a number of years ago in trying to optimally choose which hospitals to designate as level 1 or level 2 trauma centers in Korea. And so this was an optimization problem because we needed to choose a subset of the locations that you see on the map here. And for each subset that you choose, that gives you a different number of patients that you expect to be able to transport to an open trauma center within 60 minutes. And of course, you have a lot of complexities like, helicopters to site and how fast the helicopters can travel, where the patients are that need help, and so forth, and using historical data for that. Another interesting optimization problem is in the realm of online advertising. And I have a number of papers that have looked at optimally serving ads to individuals. Typically, the optimization problem is cast from the standpoint of a firm that is trying to dynamically manage many different ad campaigns for different advertisers simultaneously and balance their competing interests, their competing demands for viewer impressions or viewer clicks. So below you can see that this is a video game where there's a vending machine, and if the algorithm or the optimization method decides to put a Sprite ad on the vending machine, it will be branded as a Sprite vending machine for a certain subset of game players. All right, so that's what optimization is. Essentially, optimization is going to be implemented in a computer. So you're not going to be focused on actually solving the optimization problem, by hand or anything like that. It's as a modeler, your goal is really to understand what types of problems you can formulate algebraically and choose an appropriate software for the computer to numerically solve for an optimal solution. So the steps here are to first construct a mathematical model. You're going to use an algebraic modeling language like AMPL or GAMS or something like that. And then you're going to solve one or more instances using a solver like CPLEX or Gurobi or Nitro and so forth. And then, once you're done, there's a lot of back and forth here. So you may communicate the results to interested parties and learn from it and make changes to your model. So optimization is important to data scientists because although data scientists work a lot on predictive models, in many cases, once you have a predictive model, you're not done yet because in many cases, you may have a predictive model, for example, to model the demand curve for a given product or maybe a given class of product. But at the end of the day, once you have that predictive model, you need to use it to try and, say, maximize revenue for a company. And so the prescriptive optimization model is going to ask a question like, which products should we stock in a limited shelf space, and how should we price them simultaneously to maximize revenue? You can see here that this question really requires the predictive model as input to the prescriptive optimization model that we now need to solve. Okay, so you remember earlier I said I have two key concepts that I want to share with you today from my own experience in working with optimization models. And so the first one relates to how to select a good optimization model, because we all know that reality is really messy. And if we want a computer to find a good solution, which we call an optimal solution, to how we're going to make a plan or do something, we're going to have to approximate reality with an optimization model. So we might have for example, two optimization models which approximate reality. And let's say the first one gives an optimal value of 10. And here we're trying to say maximize revenue or something, right? And the other one gives an optimal value of 12. Well, which model would you pick? Would you say the one on the right because that gives you higher revenue? Well, maybe not, right? Because there's no guarantee that just because that the model on the right gives you a higher revenue in the model, it's going to give you higher revenue in reality if you use it in reality. And so the first thing that I want to share with you is that I'm working with real data on figuring out where to place trauma centers in Korea. In this paper, I had 3 different models: the decoupled model, the no congestion model, and then the integrated model. Now, the integrated optimization model is the most advanced, so it is a closer approximation of reality than the other 2. It's also harder to solve, as is the case when you make fewer assumptions. You typically have a harder optimization problem. But the integrated model, being closer to reality, actually has a cost that is higher than the other models, right? It actually manages to get fewer patients to open trauma centers than the other models. That's what the optimal value of those optimization models says. But those are just approximations of how well those models would perform. And what was interesting is that when we took those models and we ran a simulation to test out of sample those models, we found that no, the integrated model is in fact the best. It manages to transport the most patients to a open trauma center within 60 minutes. And so although if you just looked at the value from the optimization model, you would say, oh, it's maybe not a good model, but you really need to test the solutions to your optimization model using a simulation. And that's sort of like the same thing like you would do if you're working with data and you want to test your model out of sample. So simulation is basically something that you need to run to test your optimal solutions of an optimization model out of sample. And the picture that you should have in mind is that, the model on the left, which has a lower optimal value, it happened to be the best model in this case. It didn't need to be, but it happened to be. And on the right, you can see what's going on here is that although model 2 had the higher estimated performance, in fact, in simulation, it was model 1 that had the higher actual performance. And so we would want to choose model 1. Okay, so that's the first key insight. The second one is don't forget about opportunity costs. It's very easy to do, but it's important to realize that solvers, not only can they provide you with an optimal solution, which is like a plan or something to do, but they can tell you at the margin what the opportunity cost of each constrained resource is at the optimal solution. And this is important in many contexts, but I'm going to illustrate with an online advertising example here. So imagine that we have a number of advertisers. Here we have 4, and they have some budgets. So the advertisers are basically buying viewer impressions over time of various audience segments. And the advertisers only want their ads to be shown to specific people. So even though the website has many different people that are arriving and seeing ads, it's really only ones of that are targeted. For example, HP only wants their ads shown to students and young professionals that HP is going to be willing to pay for. Okay, so what happens is that over time, any platform that is choosing which viewer should see which ad is making some assignment of viewers to advertisers over time, like this. And the red arcs indicate which match has been actually made, or which ad has been seen by each viewer here. Now, let's imagine for a second that we know that we know the revenue for each matchup. Okay, so the first matchup that you see at the top here is $1, which means that if we actually showed the HP ad to that person, then the platform would be collecting $1 from HP. I'm going to assume here that for simplicity that we're dealing with impression-based advertising. So the revenue is just the price per impression. And let's look at a greedy example to see what this means. So for example, the first viewer arrives, which means he visits a website, and the only ad that can possibly be shown to this audience segment is the HP ad. Okay, so the assignment is easy. We just choose to show the HP ad and we collect $1. Now the second person arrives, but in this case, there's two choices. Do we want to show this person an HP ad or a Coke ad? Well, let's show that person the HP ad. Okay, we're choosing the HP ad here because it gives us $2 in revenue compared to the $1 in Coke that we could get by showing Coke. Third example, we have a third person arrive here. Same as before, we're going to choose the Starbucks ad because the revenue we can collect now is higher. And one more. Okay, now you could say, okay, this all looks good. So what can go wrong? Well, what can go wrong is illustrated in this very simple example. Remember that the advertisers have budgets. And so there is an opportunity cost of depleting each advertiser's budget that was not taken into account in the greedy example so far. So let's see what goes wrong if I continue this greedy policy here. So the first person arrives, and we're going to choose the Coke ad here because we get higher revenue from the Coke ad. That depletes Coke's budget by $2. And then we go down to the second viewer who arrives, and we would like to give this viewer a Coke ad, but Coke was willing to pay $5 here, but Coke only has $3 in budget left. So Coke is not going to buy this impression from that viewer. So we've only collected $2 in revenue here in this example, where we know if we had, changed our allocation, we would have actually collected $1 from HP and $5 from Coke, so giving us a total revenue of $6. Right? So this is the optimal assignment. So what can we do? Well, if we solve what's called a math program, this is an optimization problem here. Then we could allocate or assign a number of impressions of each viewer type to each advertiser. And that would work if we knew for sure how many viewers of each type were going to arrive or at the website, and we knew some other parameters, right? But what's more interesting here is that we can actually solve this model even if we don't know for sure what's going to happen, and extract what's called the shadow price of each budget constraint. The shadow price is something that each solver will give you. It's just as an outcome of solving the problem. And now what happens is we can use these shadow prices, which tell us at the margin how much depleting each advertiser's budget costs us as an opportunity cost. So what we do now is, in this small version of the problem, is we adjust the revenue of each matchup by its estimated opportunity cost, right? So we subtract off the shadow price here on the first edge to get an adjusted revenue of $1. We subtract off 2 times the shadow price of 80 cents to get an adjusted revenue of 40 cents. And we've subtracted off 2 times 0.8 here because we're depleting the budget by 2 units. And then we do the same thing for the third one. So I've got some adjusted revenues. And then when I go through here, what I'm going to do is I'm going to choose the HP, because now HP gives us the higher adjusted revenue. So that I've changed my decision as to who the first viewer gets matched with. And then second viewer arrives, and I choose Coca-Cola, and I collect the $6, which is the optimal solution here. Note that we actually collect the true profit, the true revenue, not the adjusted revenue. The adjusted revenue just tells us which decision to make at each point in time. Now, you might ask, does this always work? Well, we cheated a bit here because we assumed that all the parameters were known and all the matchup revenues were known. But if you have a good forecast, the shadow prices will actually be quite good. And so this highlights an important tenet, which is if you are going to run an optimization model which is based on forecasted parameters, you should strive to provide it the best forecast possible. And that concludes my talk. Again, if you want to contact anybody at the Merage School of Business, there's the contact information here. Yep.
All right. Excellent. Thank you, Dr. Turner. Appreciate the wonderful presentation that you had there. It's neat when you can take complicated stuff that maybe people can't wrap their heads around, and yet somehow you're able to put a practical example to kind of bring it to life. So that's very well done, sir. Okay, here's the question. Is Lingo good enough for optimization modeling? how would you leverage its use in the most efficient manner?
I actually don't have experience with Lingo. There's a lot of different softwares out there. My experience is that these days there are a lot of packages. Some of them are free and some of them are not. Typically, the packages that are that you have to pay for, they have many more years of industry using them, and so if you're in an application setting where an error is going to be costing you a lot of money or a lot of downtime, you might want to sort of pay for a package that has been used for 10, 20 years or so forth. Yeah.
Okay. And here's one. It's small. What differences do you see between optimizing model parameters and fitting data to model parameters? What are their individual functions, perhaps, in applying them to a technique formalism?
Okay. So if I'm fitting data to model parameters, then that itself is an optimization model. So for example, if I have even like a linear regression where I'm going to find the line of best fit through a number of points, that is an optimization model, right? So many times you may not notice it because the software you're using just has a command for run linear regression, right? So under the hood, it's an optimization model. But the second thing that you described, which is if I have an optimization model and it has a number of parameters in it, and you would want to do some parameter tuning because maybe you don't know which parameters are going to give you the best results, and you don't have any insight as to what those values should be because they're not coming from reality, right? They're not coming from any information about the world. Then you just have to try a bunch of them and see which work best, right? Sure. So I see these as complementary but different problems, basically.
Okay, very good. All right, that's all the questions we have. Dr. Turner, thank you so much for joining us this afternoon. What's the best way for people to get in touch with you?
Oh yeah, so I guess I didn't put my email address on here. My apologies. So you can contact me at john.turner@uci.edu. So it's first name dot last name at UCI, which is University of California at Irvine.edu.
And I pronounced it Irvine. It's Irvine. I beg your pardon.
No problem. Yeah. Around here, the Irvine Ranch is the big deal.
Right.
Yeah.
And I live on the East Coast, so that's what can I say? Again, sir, thank you so much for joining us, and wish you all the best.
All right. Take care. Thank you, Joe.
Yes, sir. You too.